Hello, physicists, and welcome. In this session, we'll be covering kinematics, part 3, accelerated motion. Our learning objectives are: I can draw qualitatively accurate velocity versus time graphs. I can compare velocity versus time data in terms of speed, direction, and starting position of the objects, and I can describe acceleration qualitatively and quantitatively. Please note, the parentheses indicate learning objective sections that were covered in previous videos. Let's get started. Acceleration is the rate of change of velocity. It's not concerned with how or why objects change their velocity. We're just monitoring their change of velocity. If I have an airplane that speeds up as it flies, I'm not worried about how the engines work or why the airplane flies. I'm just looking at its change of motion. If I have a car that's slowing down, I'm not worried about why it's slowing down or how the brakes work. I'm just looking at the change of its motion. It's slowing down. If I have a tree and an apple falls from that, if I'm looking at its acceleration, I'm looking at its change of velocity. I'm not worried about how gravity works. Let's take a look at acceleration the way that a mathematician would. Again, our definition of acceleration is the rate of change of velocity. Our change of velocity, we use the symbol delta to indicate a change. Change of velocity is our final velocity minus our initial velocity. And acceleration is that change of velocity divided by time. Often you'll see it as our change of velocity over the change of time. Let's do a sample calculation. We're going to look at an athlete, Usain Bolt, starting a sprint. The initial velocity at a time of 0 is 0. And in his world record sprint, he was able to cover the 100-meter dash in 9.6 seconds. His final velocity was about 14.4 meters per second. His change of velocity, we take a look at the final velocity, 14.4 meters per second, minus initial velocity, 0. His change of velocity, or another way of saying it, he increased his velocity from 0 to 14.4 meters per second. His change of velocity was plus 14.4 meters per second. He was moving to the right. Acceleration is that change of velocity divided by the change of time, or the elapsed time for his race, 9.6 seconds. 14.4 divided by 9.6 is plus 1.5, and now we have very interesting units, meters per second per second. What does that mean? That means I'm going 1.5 meters per second faster every second. 1.5 meters per second per second. We'll go through a more thorough practice calculation now. And just a reminder that our velocity is our change of position divided by our change of time. We have a car that's starting at a position of 2 meters at a time of 0. We'll mark the position of the car every 2 seconds along this number line. After 2 seconds, it's at position of 3. After 4, it's a position of 6. After 6 seconds, it's at 11. And after 8 seconds, it's at 18 meters. Our ruler and timestamps provide a good record of where the car was at various times. Let's transfer this information into a table. Again, we see our ruler and timestamps down at the bottom, and then that information has been transferred into this table. Time at a time of 0 is the position of 2 meters. At 2 seconds, it was at 3 meters, and so on. Now we need to record the velocity over each time interval. To get that, we need the change of position over our change of time. Let's go and calculate our change of position over each of these time intervals. So from 0 to 2 seconds, I went from 2 to 3 meters, so my position changed 1 meter. From 2 to 4 seconds, I went from 3 to 6 meters. My position changed by 3 meters. From 4 to 6 seconds, I moved 5 more meters, and from 6 to 8, moved another 7 meters. Notice that there's no entry in the first line because we have to look over an interval, and there's no interval in the first position. Let's go and calculate our velocity from 0 to 2 seconds. Our velocity is the distance we traveled over that interval, 1 meter, and divided by the time. We're going from 0 to 2 seconds. We'll transfer that information over to our calculation. 2 seconds, 1 meter divided by 2 seconds is positive 0.5 meters per second. For the next line, we traveled 3 meters divided by our 2 seconds, from 2 to 4 seconds. Our average speed over this next time interval is 1.5 meters per second, and so on for the next 2 time intervals, 2.5 and 3.5 meters per second. The data in this table will be transferred to a new table so that we can calculate acceleration information. And here we have it. The acceleration is the change of velocity over the change of time. So we'll look at the change of velocity from 2 to 4 seconds, and we'll record that as being 1 meter per second is the change in the velocity. From 4 to 6 seconds, the change of velocity went from 1.5 to 2.5 meters per second, so 1 meter per second. And again, from 6 to 8, we went from 2.5 to 3.5 meters per second. To calculate acceleration, we take that change of velocity and divide it by the change of time. Let's take a look at what the average acceleration was from 2 to 4 seconds. So I take my change of velocity plus 1.2 meters per second, and I have to divide that by the change in time from 2 to 4 seconds. Let's bring it on over to the right side. Divide that by 2 seconds, and I have, I'm going to draw it up here, 0.5 meters per second per second. What does that mean? On average, I'm increasing my speed 0.5 meters per second every second. For the 2 seconds, 0.5 meters per second plus 0.5 meters per second means I increased my speed 1 meter per second. And I'll end up doing those calculations for the last two, from 4 to 6, and from 6 to 8 seconds. Our acceleration was 0.5 meters per second per second. We'll transfer all this data to a new table. And here it is for our time, position, change of position, velocity, change of velocity, and acceleration. I want to produce 2 graphs. Our first one will be a position versus time graph. We'll look at our time will be our independent variable that goes along, and then we are measuring the position at various times. Because time is our independent variable, it'll go along the horizontal axis. So let's put time along the horizontal axis. We have to cover the time interval from 0 to 8 seconds. We see our grid has 10 divisions, so it looks like 1 second per division will work out nicely. And I need to remember to list my unit, so it's time in seconds. That means our dependent variable, which will go on the vertical axis, will be our position. Measured in meters. We have to cover up to 18 meters. I have 10 divisions. It looks like about 2 meters per division will work out well. So let's add those in there. Let's put in our data points. I have 0 and 2, 2 and 3, 4 seconds and 6 meters, 6 seconds and 11 meters, 8 seconds and 18 meters. Take a look at this data closely, and it does not lie on a straight line. And let's see, if I try my best fit line through there, I get a special type of curve that looks like that. In math, you're starting to look at these. This shape is known as a parabola. Time to produce now the velocity versus time graph. Our independent variable will be time again, and our measured quantity will be our velocity at various times. Because time is our independent variable, we'll put that along the horizontal axis, measured in seconds. We're going from 0 to 8 seconds, so again, it looks like 1 second intervals work out well. Our dependent variable is the speed at various times. So we'll put, I shouldn't have said speed, we'll call it velocity. Our velocity along the vertical axis. In this case, we only have to cover up to 3.5 seconds. So it looks like probably about half a meter per second per division would do pretty nicely. And we'll just label every other division just to keep it a little bit cleaner here. Now let's go ahead and start plotting those points on here. Again, notice that we won't have anything at 0 seconds because we don't have an average velocity at 0. If we had a car speedometer, that gives us our instantaneous velocity, but this one we were just averaging it over a period of time. So let's go ahead and add those to the graph. So your point at, let's say at 2 seconds and half a meter, 4 seconds and 1.5 meters per second, 6 seconds and 2.5 meters per second, and at 8 seconds, the average speed was 3.5 meters per second. Let's draw a best fit line through that. Straight line does a nice job of fitting through that. Hey, earlier we were looking at our acceleration as the rate of change of velocity. And back in our graphing, we know that a slope tells us the rate of change of the dependent variable compared to the independent variable. So let's take a look at the slope of this line. If we look at our rise over run, we find that it is 0.5 meters per second. So that's meters per second. Let's try applying this information in a new situation. All right. Let's take a look at that car. As before, it'll start at a position of 0, but in this case, it's already moving. Well, again, we'll mark it at various times. We can see that the car is slowing down, moving forward, but slowing down. You can come back and refer to this slide. But what we'd like to do is take a look at what type of graphs this would produce for a position versus time. Time will be on the independent or the horizontal axis as the independent variable, and our position along the vertical axis. Let's take a look at the velocity versus time, again with time on the horizontal axis as the independent variable, and our velocity along the vertical axis. And we'll set those, let's see, R0 or origin points down in the lower left-hand corner. What I'd like you to do is go back through that data and get a general idea of what the shape of each of these graphs would look like. If you want to plot all the data exactly, you can, or you can get a general shape of these. So I'd like you to, at this point, pause the video and go ahead and try that out. I'll come back with an answer in just a little bit. Hey, so welcome back. All right. Let's take a look at our position versus time graph. We know that the car kept going forward, so therefore the position was increasing, but as it went along, the amount of increase kept getting less. You should have produced some type of a curve that looked like this, always increasing, but as it went along, got less and less increase. Let's take a look at the velocity. It was always moving forward, so we know that it always had a positive velocity, but it started off fast and got slower and slower. Hopefully you got something that looked like that. Hey, so let's wrap things up now. All right. Hey, so can you now draw qualitatively accurate velocity versus time graphs? Compare velocity versus time data in terms of speed, direction, and starting position of the objects. And can you describe acceleration qualitatively and quantitatively? For now, that's physics.